Hello, everyone, and a very warm welcome to Kognito Key. I'm absolutely thrilled to have you here with us today. So, in this explainer, we're going to be unlocking the real foundational materials of modern electronics. You know, those wires, diodes, and rubber insulators? They're literally the silent heroes powering our entire digital world. And today, we're breaking down exactly how they work. Let's just dive right into our roadmap for today. We'll kick things off with basic conductivity. Move right through the three main material types, explore this super fascinating thing called the forbidden energy gap, compare their physical differences, and then, of course, wrap it all up with some real-world applications. All right, Section 1, Understanding Electrical Conductivity. To really get started here, we need to lay down a solid foundation and ask a pretty fundamental question about how energy actually moves. So, the big question that probably strikes your mind is this. What exactly allows current to flow so effortlessly through a copper wire, but then completely stops dead when it hits a piece of rubber? Like, what is the invisible mechanism at play here? Well, it brilliantly comes down to this definition right here. Conductivity is all about the movement of electrons. Think of something called the valence band as the electron's comfy home, and the conduction band as a super fast highway. When you apply voltage, it basically acts as a pushing force, trying to kick those electrons out of their home and onto that highway. If they can make that jump, boom, electricity flows. Moving on to Section 2, let's officially meet the three material types. These are basically the main characters of our electronics story, and we're going to see how they handle those moving electrons. Notice how each of these materials behaves so differently. Conductors, they permit a super easy flow simply because they're packed full of free electrons. Insulators, on the other hand, almost zero flow. But semiconductors are kind of the wild cards here. Their moderate flow actually relies on a combination of both electrons and what we call holes. And those holes are essentially just empty spaces left behind by the moving electrons, which actually help carry the charge. Pretty cool, right? Okay, Section 3, the forbidden energy gap. This is the absolutely crucial point that truly separates these three materials from one another. I want you to think of this forbidden energy gap kind of like a bridge. It connects the valence band to the conduction band. Now, for conductors, the gap is literally 0 electron volts. The bands just overlap, making it a perfectly seamless bridge. For semiconductors, those electrons have to pay a tiny toll, about 1 electron volt, to cross over. But our insulators, they have this massive, practically uncrossable 5 electron volt chasm. Under normal conditions, electrons simply cannot make that jump. No way. And because conductors have absolutely 0 energy gap, their conduction band is just completely filled with charge carriers that are ready to move at a moment's notice. This is a huge contrast to the completely vacant conduction band of an insulator. In an insulator, all those potential charge carriers are basically trapped behind that massive energy gap we were just talking about. That brings us to Section 4, Key Differences Compared. Let's see how all this underlying physics translates into the actual physical properties we deal with in engineering. Now, let's talk about a truly fascinating property here, the temperature coefficient. We already know conductors have low resistivity and insulators have high resistivity, but look at how they react to temperature. Conductors have a positive coefficient, which means their resistance actually increases as they heat up. But check this out. For semiconductors and insulators, they have a negative coefficient. That means their resistance actually decreases as they get hotter. It's because the heat literally gives their electrons the extra burst of energy they need to finally jump that forbidden gap. All right, Section 5, Conclusion and Summary. We've totally geeked out on the physics and electron behavior, so let's tie it all together and see where these materials show up in our everyday lives. Let's look at the purely practical side of all that theory. Your pure conductors, things like copper and aluminum, they act as the highways, constantly conducting power through wires. Then your semiconductors, mainly silicon and germanium, they're like the traffic lights. They act as the diodes and transistors processing all the electricity inside your computers and phones. And finally, your insulators, like rubber and glass, they are the safety barriers. They keep all that powerful current exactly where it belongs so that you and I stay safe. So, to summarize our whole explainer today, here is your ultimate takeaway. The ability of electrons to jump from the valence band to the conduction band dictates the conducting level of the entire material. It's all about that jump. But you know, it really begs the question, as we engineer crazy new nanomaterials and keep pushing the boundaries of quantum physics, how long is it going to take until we discover materials that just break these rules entirely? Thank you so much for joining me here at Kognito Key today. If you found this breakdown valuable, please make sure to subscribe to the channel and like and share this video with your friends.
Keep learning, keep exploring, and I'll catch you in the next one.